Welcome! Today, we will dive into an exciting coding problem, problem number 683, K empty slots. Stay tuned as we explore the problem, break it down step by step, and analyze potential solutions. Let's get started. In this problem, you are given an array called bulbs, where each element represents the day on which a specific bulb turns on. These bulbs are lined up in a straight row, numbered sequentially from 1 to n. Each bulb can either be turned on or off. The central goal of this problem is to find a specific pattern called a K-empty slot. A K-empty slot occurs when two bulbs are turned on, and there are exactly K positions between them where all bulbs remain off. Your task is to determine the earliest day when this condition is met. If such a day doesn't exist, the function should return -1. To solve this, you are given two inputs, the bulbs array and an integer k, which specifies the number of empty slots required. The output will be a single integer indicating the earliest day when a k-empty slot occurs, or -1 if it never happens. Let's look at an example to clarify this. Suppose the bulbs array is 1, 3, 2, and k is 1. On day 1, the bulb at position 1 turns on, so the row looks like 1, 0, 0. On day 2, the bulb at position 3 turns on, so it becomes 1, 0, 1. At this point, we have two bulbs turned on, with exactly one off bulb between them, which satisfies the condition for a k-empty slot with k equals 1. Therefore, the output is 2, as this condition is first met on day 2. Now consider a different example where the bulbs array is 1, 2, 3, and k is again 1. On day 1, the bulb at position 1 turns on, resulting in 1, 0, 0. On day 2, the bulb at position 2 turns on, so the row becomes 1, 1, 0. Finally, on day 3, the bulb at position 3 turns on, making the row 1, 1, 1. At no point do we see two bulbs turned on with exactly one empty slot between them. Therefore, the answer is -1 because the condition for a k-empty slot is never satisfied. Now let's examine a larger example. If bulbs is 6, 5, 8, 9, 7, 1, 10, 2, 3, 4, and k is 2, the earliest day when a k-empty slot occurs is on day 8. On this day, there is a valid configuration where two bulbs are turned on with exactly two off bulbs between them. Finally, there are a few important constraints and edge cases to keep in mind. The array bulbs is always a permutation of numbers from 1 to n, and k is guaranteed to be less than n. For edge cases, if k is 0, any two consecutive bulbs turning on will meet the condition. Conversely, if the array has just one bulb, the answer is always -1 since it's impossible to form a pair of turned-on bulbs. Similarly, if k is close to n, such as k equals n1, the only scenario for a k-empty slot is when the first and last bulbs are on, with all others off in between. To begin, the brute force approach is the most straightforward way to tackle this problem. The intuition here is to simulate the process of turning on the bulbs day by day and then check all possible pairs of bulbs to see if they satisfy the condition of having exactly k unlit bulbs between them. The process involves iterating over all pairs of bulbs, ensuring that the two selected bulbs are already turned on, and then confirming that the bulbs between them remain unlit. Once we find a valid pair, we return the earliest day this occurs. While this method is simple and easy to understand, it has a significant drawback. The time complexity is n squared, as we have to examine all pairs of bulbs. This makes the approach highly inefficient for larger inputs, such as when n reaches 10,000 or more. Additionally, while the space complexity is minimal at 1, the lack of scalability makes this method impractical for real-world scenarios with large input sizes. Now, to improve efficiency, we can use the sliding window approach. The key idea here is to maintain a fixed size window that allows us to check for valid intervals in a more systematic and efficient manner. First, we construct an array called days, where each entry represents the day a specific bulb is turned on. Next, we use two pointers to define a sliding window of size k plus 1. The goal is to check if all the bulbs within this window, excluding the ends, remain unlit. If this condition is met, we can determine the day based on the maximum of the two end bulbs. We continue sliding the window across the array until either a valid interval is found or the entire array is traversed. This approach significantly reduces the time complexity to n, as each bulb is processed only once. However, it requires additional space to store the day's array, making the space complexity n. While this method is faster, it comes with trade-offs, such as requiring a clear understanding of window boundaries and careful handling of indices. Additionally, the tree set or balanced binary search tree approach provides another efficient way to solve the problem. The intuition here is to use a tree set to maintain the indices of bulbs that are turned on in a sorted order, allowing us to quickly locate the nearest neighbors for any given bulb. For each bulb that is turned on, we add its index to the tree set and then use it to find the closest bulbs to its left and right. These neighbors are then checked to see if they satisfy the k-empty slots condition. If they do, the corresponding day is returned. The time complexity of this approach is O, n log n, as tree set operations like insertion and search take O, log n, and we perform these operations for each bulb. The space complexity is O, n, as we store the indices in the tree set. While this method is slightly slower than the sliding window approach due to the logarithmic overhead, it is still efficient and provides a practical alternative. However, it requires familiarity with tree set or balanced binary search trees, which may make the implementation less intuitive for some. Finally, the sliding window approach emerges as the most balanced and effective strategy for solving this problem. Its optimal time complexity of O, n, and relatively straightforward implementation make it an excellent choice. By processing each bulb only once and focusing on valid windows through efficient checks, this method minimizes unnecessary computations. The key insight lies in the days array, which allows us to track the order in which bulbs are turned on. This enables us to quickly verify if any given window satisfies the problem's conditions. Moreover, the sliding window technique ensures that we only focus on relevant sections of the array, making the process both fast and space efficient. Compared to the tree set approach, the sliding window method avoids the added log n overhead, though it does require O, n, extra space for the days array. While careful handling of indices and boundaries is necessary, this can be managed with a clear plan. Overall, the sliding window approach strikes the best balance between efficiency, clarity, and practicality, making it the ideal choice for tackling the k-empty slots problem. The problem we're tackling is to determine the earliest day when two bulbs that are turned on have exactly k bulbs between them that are still off. To break this down, we are given an array called days, where each element represents the day a specific bulb is turned on. For example, if days equals 3, 1, 2, bulb 1 turns on day 3, bulb 2 on day 1, and bulb 3 on day 2. Alongside this, we have two important parameters, n, the total number of bulbs, and k, the number of bulbs that must remain off between two turned-on bulbs to satisfy the condition. To solve this, we initialize a Boolean array called turned_on of size n, with all values set to false. This array helps us track which bulbs are turned on as we process days day by day. Using this setup, we aim to simulate the process of turning bulbs on and check for valid pairs that meet the criteria. Now we proceed with simulating the process of turning on the bulbs day by day. For each day in the days array, a specific bulb is turned on. We update the turned_on array to reflect this by setting the corresponding index to true. As we process each day, we also check for pairs of bulbs that satisfy the condition. To do this, we iterate through all bulbs to find the first bulb I that is turned on. For each such bulb, we then look for another bulb j to the right of I that is also turned on. Once we identify two turned-on bulbs, we check two things: first, that there are exactly k bulbs between I and j, and second, that all these intermediate bulbs remain off. If we find such a pair, we immediately return the current day. If no such pair exists after processing all days, we return -1, indicating that the condition was never met. To analyze this approach, the brute force method involves iterating through all pairs of bulbs, I, j, for each day, leading to a time complexity of O, n squared. While this is straightforward, it becomes computationally expensive as the number of bulbs increases. There are also important edge cases to consider. For instance, if k is greater than n, it's impossible to find a valid pair because there aren't enough bulbs to satisfy the condition. Similarly, if all bulbs are turned on consecutively, no pair will meet the requirement. To improve efficiency, we can implement an early exit strategy. If a valid pair is found, we stop the simulation immediately. The turned_on array plays a crucial role here, allowing us to check the state of any bulb in constant time. Together with the days array, these structures form the backbone of our simulation. Let's illustrate this with an example where days equals 2, 1, 3, 5, 4, and k equals 2. On day 1, bulb 2 is turned on, but no pairs exist yet. On day 2, bulb 1 is turned on, and we check the pair 1, 2, but it doesn't satisfy the condition. On day 3, bulb 3 is turned on, and we check pairs 1, 3, and 2, 3, neither of which meet the criteria. On day 4, bulb 5 is turned on, and we evaluate pairs like 1, 5, 2, 5, and 3, 5, but still no valid pair is found. Finally, on day 5, bulb 4 is turned on, and the pair 2, 5 satisfies the condition with exactly 2 bulbs off between them. Thus, the result is day 5. To optimize this process, we can use a sliding window of size k+1 to focus only on relevant bulbs, reducing unnecessary computations. Additionally, binary search can be employed to locate potential pairs more efficiently if the bulbs are processed in sorted order. To summarize, while the brute force approach provides a simple and clear solution, its quadratic time complexity makes it impractical for larger inputs. By incorporating optimizations like sliding windows or binary search, we can significantly improve performance, especially in scenarios where efficiency is critical, such as competitive programming. These optimizations enable us to handle larger datasets without sacrificing correctness, ensuring that the solution remains robust and scalable. This solution uses a sliding window approach to find the earliest day when there are exactly k empty slots between 2 bulbs that are turned on. First, we create an array days to record the day each bulb is turned on. Next, we initialize 2 pointers, left and right, to represent the window of bulbs being checked. We iterate through the bulbs, checking if all bulbs between left and right are turned on later than the bulbs at the edges of the window. If this condition is satisfied, we update the result with the maximum day of the 2 edge bulbs. Otherwise, we move the window forward to skip invalid bulbs. The function finally returns the earliest day or -1 if no such arrangement exists. Here, we start by importing the necessary Java utilities and defining our solution class. The method kEmptySlots takes 2 parameters, an array of integers bulbs, which represents the order in which bulbs are turned on, and an integer k, which specifies the required number of empty slots between 2 bulbs. First, we determine the number of bulbs, n, and initialize an array days of the same size. The days array will help us track the day each bulb is turned on. For example, if bulb 3 is turned on day 1, then days 2 will store the value 1. Next, we set up 2 pointers, left and right, to define a sliding window that spans k+1 bulbs apart, and initialize result to integer.max_value to store the minimum day that meets our condition. The while loop processes the window as long as right is within bounds. Inside the loop, we use a flag, valid, to check whether all bulbs between left and right bloom later than the bulbs at the endpoints. If we find a bulb that violates this condition, we reset the window by moving left to the invalid position and adjusting right accordingly. If the condition holds, meaning the bulbs between left and right bloom after both endpoints, we calculate the day by taking the maximum of days, left, and days, right, and update result with the smaller of its current value or this calculated day. Then, we move the window forward by setting left to right and recalculating right as left plus k+1. Finally, once the loop completes, we return the result. If no valid day is found, result will remain integer.max_value, and we return -1, otherwise, we return the minimum valid day stored in result. This approach efficiently finds the earliest day that satisfies the condition by leveraging the sliding window technique and the pre-computed days array. To solve this problem, we start by analyzing the first example where bulbs are given as 1, 3, 2, and k=1. The goal is to find the earliest day when there's exactly 1 empty slot between 2 blooming flowers. The first step is to create a days array that tells us on which day each bulb blooms. Initially, the array is set to 0, 0, 0. On day 1, bulb 1 blooms, so we update the first position to 1, resulting in days equals 1, 0, 0. On day 2, bulb 3 blooms, updating the third position to 2, so now days equals 1, 0, 2. Finally, on day 3, bulb 2 blooms, and we update the second position to 3, giving us days equals 1, 3, 2. Next, we perform a sliding window search. The window is initialized with left equals 0, right equals k+1 equals 2, and result equals INF. For the first window, we check the bulbs between the left and right indices, which means examining days 1 equals 3. Since 3 is greater than the maximum of the bloom days at the left and right ends, which is max, 1, 2, equals 2, the condition fails. We then shift the window by incrementing left to 1 and right to 3. With the updated window, right now exceeds the bounds of the array, meaning there are no more valid windows to check. As a result, no valid day exists where there's exactly one empty slot between two blooming flowers in this example. Therefore, we return -1. Now, let's analyze the second example where bulbs are 1, 2, 3, and k equals 1. Again, the goal is to check if there's a day when exactly one empty slot exists between two blooming flowers. We start by creating the days array. Initially, it is 0, 0, 0. On day 1, bulb 1 blooms, so we update the first position to 1, resulting in days equals 1, 0, 0. On day 2, bulb 2 blooms, and we update the second position to 2, giving us days equals 1, 2, 0. Finally, on day 3, bulb 3 blooms, and we update the third position to 3, resulting in the final days equals 1, 2, 3. Next, we perform the sliding window search. The window is initialized with left equals 0, right equals k plus 1 equals 2, and result equals INF. For the first window, we examine the bulb between the left and right indices, which is days, 1 equals 2. Here, 2 is less than the maximum of the bloom days at the left and right ends, which is max, 1, 3, equals 3. Because the condition fails, we shift the window by incrementing left to 1 and right to 3. However, at this point, right exceeds the bounds of the array, so no more valid windows exist. Thus, no valid day exists where there's exactly one empty slot between two blooming flowers in this example. As a result, we return -1. Now, let's examine a more complex example where bulbs are 6, 5, 8, 4, 7, 2, 9, 1, 3, and k equals 2. The task remains the same: find the earliest day when there are exactly two empty slots between two blooming flowers. We begin by creating the days array, which is initialized as 0, 0, 0, 0, 0, 0, 0, 0, 0. As we process the bulbs array, we determine the bloom day for each bulb. On day 1, bulb 6 blooms, so we update the sixth position to 1, resulting in days equals 0, 0, 0, 0, 0, 1, 0, 0, 0. On day 2, bulb 5 blooms, so we update the fifth position to 2, giving us days equals 0, 0, 0, 0, 2, 1, 0, 0, 0. On day 3, bulb 8 blooms, so we update the eighth position to 3, resulting in days equals 0, 0, 0, 0, 2, 1, 0, 3, 0. Repeating this process for all bulbs, we eventually get a final days array of 8, 6, 9, 4, 2, 1, 5, 3, 7. Next, we initialize the sliding window with left equals 0, right equals k plus 1 equals 3, and result equals INF. For the first window, we examine the bulbs between the left and right indices, which are days, 1 equals 6 and days, 2 equals 9. Both these values are greater than the maximum of the bloom days at the left and right ends, which is max, 8, 4 equals 8. Since the condition holds, we update the result to min, result, max, days, left, days, right, equals min, INF, 8, equals 8. We then shift the window by incrementing left to 3 and right to 6. In the second window, the condition fails, so we shift the window again, setting left to 4 and right to 7. At this point, no more valid windows meet the condition. Therefore, the earliest day where there are exactly two empty slots between two blooming flowers is day 8. This concludes the solution for this example. The time complexity of the solution begins with the pre-processing step where we construct the days array. Here, for each bulb in the bulb's input array, we determine the day it gets turned on and store that in the days array. This traversal is linear, as it iterates through all n bulbs once, resulting in a time complexity of O(n). Next, the sliding window traversal begins. The window is defined by two pointers, left and right, which initially span the length of k plus 1. For each window, the algorithm checks whether the bulbs between the left and right pointers meet the condition for exactly k empty slots. If the condition fails, the window is shifted, and the process repeats. While this involves iterating over the bulbs within the window, the total number of iterations across all windows is limited to O(n), as each bulb is visited at most once. This dynamic update ensures that the overall time complexity of the sliding window traversal is also O(n). When we combine the pre-processing step and the sliding window traversal, we find that both contribute linearly to the total computation. Therefore, the overall time complexity of the solution is O(n). Now, turning to space complexity, the algorithm creates an auxiliary days array of size n to store the day each bulb is turned on. This array takes O(n) space. Aside from this, the algorithm uses a few additional variables such as left, right, result, and valid. These variables consume constant space, denoted as O(1). Since the dominant factor is the days array, the overall space complexity of the solution is O(n). To understand the efficiency of this approach, let's compare it to the brute force solution. A naive approach would involve checking every possible pair of bulbs to determine if they satisfy the condition of having exactly k empty slots between them. This would require nested loops, where one loop processes each bulb while the other iterates through all other bulbs, resulting in a time complexity of O(n²). However, the brute force approach uses no additional data structures, so its space complexity remains O(1). By contrast, the optimized sliding window approach eliminates the need for nested loops. Instead, it dynamically adjusts pointers and skips invalid ranges, ensuring that each bulb is processed only once. This reduces the time complexity to O(n), while the space complexity remains O(n) due to the days array. Thus, the optimized approach is significantly more efficient for larger inputs. Analyzing the solution further, we can consider the best, average, and worst-case scenarios. In the best case, the algorithm finds a valid window early, requiring minimal adjustments to the left and right pointers. Here, the time complexity is O(n), as the array is still traversed linearly. For the average case, the algorithm processes the array with occasional adjustments to the window, but the total traversal remains linear, so the time complexity is still O(n). In the worst case, the condition fails frequently, resulting in multiple adjustments to the sliding window. However, even in this scenario, the dynamic nature of the pointers ensures that the total work done is proportional to the size of the array, maintaining an overall O(n) time complexity. To confirm the O(n) time complexity, we can look at the underlying mechanics of the sliding window approach. The left and right pointers increment dynamically and never move backward, ensuring that each index in the days array is visited at most once. While the inner loop examines up to k elements for each window, the total number of windows is bounded by n/k+1. This means the total number of checks performed by the inner loop is proportional to n. As a result, the algorithm's operations scale linearly with the size of the input, solidifying its O(n) time complexity. When working on the k empty slots problem, there are some common mistakes to watch out for. One frequent issue is ignoring edge cases. For instance, when the value of k is 0 or the number of bulbs is less than 2, the problem may behave differently, so it's important to validate input constraints to avoid runtime errors. Another challenge is inefficient pair checking. A naive approach that checks all possible pairs of bulbs for every day has a time complexity of O(n²) or worse. This can become impractical for large input sizes, such as when n exceeds 10,000. Instead, optimizing with data structures like arrays, sets, or trees is critical. Additionally, misunderstanding the problem statement can lead to incorrect solutions. For example, assuming bulbs don't need to be turned on in a specific order can result in invalid arrangements. It's helpful to carefully rephrase the problem in your own words to clarify its requirements. Lastly, off-by-one errors are another common pitfall, where the range of bulbs between two indices might be miscalculated due to confusion between zero-based and one-based indexing. Always double-check how ranges are defined to avoid these errors. Now, another important consideration is time complexity. Even if your solution is logically correct, an unoptimized O(n² approach will fail for large inputs, leading to time limit exceeded errors. Breaking down the complexity of your solution ensures it can scale to handle larger datasets. From an interview perspective, optimization should be a key focus. Start with a brute force approach to clarify your thought process, but be ready to pivot to optimized solutions quickly. Discuss the trade-offs involved, particularly in terms of time and space complexity. Recognizing patterns is another critical skill. Many solutions to this problem involve sliding window techniques, prefix sums, or greedy strategies. Identifying these early can save you significant time. Clear communication is equally important. As you work through possible approaches, explain your thought process, including how you eliminate invalid solutions or optimize pair checking. Finally, choosing the right data structure is often key. For example, sets, heaps, or segment trees are commonly used here because they allow efficient tracking and querying of bulb states. This problem also has strong connections to other LeetCode challenges, which can serve as excellent practice. For example, LeetCode 683, the k-empty slots problem itself, focuses on efficiently implementing sliding window techniques or tree-based solutions to solve similar challenges. Another related problem is LeetCode 852, peak index in a mountain array. While this is a binary search problem, it also involves identifying patterns within array indices, which is a transferable skill. LeetCode 406, queue reconstruction by height, is another great example. It requires sorting and using greedy algorithms, which are valuable for practicing optimization strategies relevant to k-empty slots. Lastly, LeetCode 239, sliding window maximum, is a classic problem that involves sliding windows and optimized data structures for range queries. By solving these related problems, you can strengthen your ability to recognize patterns and develop techniques that apply to a broader range of challenges. Finally, let's discuss alternative approaches and the trade-offs they involve. Using a sliding window technique is often highly efficient for problems requiring sequential analysis of subarrays. It typically reduces the time complexity to O(n), but you'll need to handle edge cases carefully to avoid bugs. Another approach involves binary search combined with tree-based data structures. This method is highly optimized for range queries, such as finding the nearest bulb, but it can be more complex to implement and may require additional coding time during an interview. Brute force, on the other hand, is simple and intuitive to implement, making it useful for small-scale testing or debugging. However, it's inefficient for large inputs and rarely suitable for final submissions. The key takeaways here are to prioritize optimization early, as brute force solutions are unlikely to meet competitive coding standards. Choosing the right data structure, such as sets, heaps, or segment trees, can significantly improve efficiency for range queries. Also, clear communication is vital. Be prepared to explain your assumptions, how you handle edge cases, and the steps you took to optimize your solution. Finally, practicing related problems will help you build a strong foundation for recognizing patterns and solving similar challenges more efficiently. Thank you for joining me on this journey to solve k-empty slots. We discussed brute force and optimized approaches, their complexities, and the key takeaways from the problem. If you found this helpful, make sure to like, subscribe, and stay tuned for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!